Welcome back to Introduction to Higher Mathematics. In our last lecture, we dug a bit deeper into relations. We defined relations that are left unique versus right unique, relations where you always know where you came from versus you always know where you're going, and left total versus right total, where the domain has nothing left out versus the codomain has nothing left out. From here, we define the familiar concept of a function as a relation that must be both left total and right unique. We learned how to notate functions, both the prototype and the definition. We talked about the image of a point in the domain, and extended it to both the image of a subset of the domain and the image of the entire domain, the last of which we called the range. We also reversed direction and looked at the pre-image of a value of the codomain, from which we created the inverse of a relation. We added more properties to functions like left uniqueness, which makes them injective, and right totality, which makes them surjective, or even both, which makes them bijective. We saw that bijective functions were special, as they show that two sets are the same size, and their inverses are guaranteed to be functions as well. We briefly looked at composition of functions, taking special note that a function composed with its own inverse is the identity function, as long as the function is bijective. Finally, we cleverly restricted the domain and codomain to obtain functions with the properties we want. In this lecture, we're going to be exploring number theory, one of the oldest fields of mathematics. Throughout history, humans have strived to learn more about the properties of numbers. Through pondering, investigating, experimenting, and postulating, and with a little bit of creativity and luck, we've come to know as much as we do today. But it's important in our study of mathematics not to take things for granted, because things that we don't even bother to question today were true points of contention in older times. For instance, when we first talked about set theory, we introduced the set Z of integers, which extended the natural numbers by including their negative counterparts as well as zero. Nowadays, we hardly even bat an eye at negative numbers. We use them all the time for really cold temperatures, overdrawn bank accounts, and charges of electrons. But the concept of a negative number as an actual thing seemed ludicrous to the ancient Greeks. Enter the Alexandrian Greek mathematician Diophantus, the author of the book Arithmetica that Fermat was reading when he made his conjecture about sums of powers. In Arithmetica, Diophantus wrote about an equation that today would be translated as 4x plus 20 equals 0. We of course know that the solution to this would be x equals negative 5, but Diophantus dismissed the equation entirely, calling it absurd. Descartes, in his La Géométrie, also threw out negative solutions to such equations, calling them racines fausses, or false roots. This sort of mentality that negative numbers were mere nonsense persisted throughout Europe until the 17th century. Not all cultures were quite so closed-minded, though. The first appearance of negative numbers in history was in 9 chapters on the mathematical art during the Han Dynasty, in which Chinese mathematician Liu Hui recorded the Chinese practice of using red counting rods for positive numbers and black rods for negative numbers, the opposite of our convention in finance today, in which black numbers are positive and red numbers are negative. In 7th century India, negative numbers were equally common, and were frequently used in problems involving debts. The Indian mathematician Brahmagupta even used negative numbers to derive the quadratic formula. By the way, the Indians were also the first culture to understand zero as a number. The word zero even comes from a translation of the Sanskrit word shunya, meaning empty. If negative numbers and zero were strange concepts for humanity to wrap its collective head around, then imaginary numbers were downright mind-boggling. The first times that the square roots of negative numbers were really considered was in the 16th century, when mathematicians in Italy were seeking general solutions to cubic and quartic equations. The story behind this is a fascinating one, in which hot-headed men were battling each other. Well, not literally fighting, but fighting by showing off their ability to solve polynomial equations in a public arena. Italian mathematician Girolamo Cardano discussed them in his text Ars Magna, the Great Art, in which he posited an equation, x times 10 minus x equals 40, for which he correctly found the solutions 5 plus the square root of negative 15 and 5 minus the square root of negative 15, which we would today write as 5 plus I root 15 and 5 minus I root 15. As he wrote in his text, putting aside the mental tortures involved, Multiply 5 plus root negative 15 by 5 minus root negative 15, making 25 minus negative 15, whence the product is 40. He added, "So progresses arithmetic subtlety, the extreme of which, as is said, is as refined as it is useless." It was Descartes that actually gave these square roots of negative numbers the term imaginary when he was considering the intersection of a parabola and a circle. And finally, if this circle neither cuts nor touches the parabola at any point, it testifies that there is neither a true nor a false root of the equation, and they are all imaginary. But in reality, there's nothing imaginary about them. They very much exist and are constantly used in engineering and physics. For instance, in an AC current, a purely imaginary voltage can still give you quite a real shock. The fact that the square roots of negative numbers are still known today as imaginary numbers is a testament to how much of a struggle it's been for humans to understand the numbers we work with every day. And this struggle isn't over. It's still ongoing, and mathematicians every day are still hard at work trying to solve the mysteries of numbers. With that in mind, let's begin our exploration of number theory. Number theory starts off with some rather simple concepts. In fact, it's the simplicity of number theory that makes it so deceiving. Generally, we'll only be working with the set of integers. Suppose we have two integers, call them a and b. Then if we can find an integer q such that a equals b times q, then we say b divides a. So for example, suppose a were 12 and b were 3. Is there an integer solution to 3q equals 12? Of course, q would be 4. So we'd say that 3 divides 12. We usually reference this with a vertical bar. Be careful not to confuse this with a fraction bar. We sometimes say a is divisible by b. From these, we can build two important sets. First of all, the set of all integers b such that b divides a is called the set of factors or divisors of a. So for example, the divisors of 12 are 1, 2, 3, 4, 6, 12, and their negative counterparts. Generally, though, we'll only be considering positive divisors from here on out. Second of all, the set of all integers c such that a divides c is called the set of multiples of a. So for example, the multiples of 12 are 12, 24, 36, and so on, as well as 0, negative 12, negative 24, and so on in the other direction. Now, sometimes one number doesn't divide another. Take 3 and 14, for example, and consider the equation 3q equals 14. If we were using rational numbers, then we could just let q equal 14 thirds and be done with it. But since we're restricting ourselves to only integer solutions, we have to conclude that this equation has no solution in the integers. We can get rather close, though. We can find a q that'll be just a bit too small, and another q that'll be just a bit too large. So if q equals 4, then 3q equals 12. And if q equals 5, then 3q equals 15. Now, suppose we took the lesser value of q. How much more would we have to add to get to our goal of 14? The answer would be 2. So while there's no way to write 14 as 3 times some integer, we can say that 14 equals 3 times 4 plus an extra 2. This is called Euclidean division, and it's true for any integers a and b, as long as b isn't 0. We can always represent a in the form q times b plus r, where r is non-negative and less than b. We call q the quotient and r the remainder. So, with this in mind, we can say that b divides a if and only if the remainder is 0. Now, again, let's say we have two non-zero integers. Let's make a equal 18 and b equal 24. We could list out the divisors of each number. Notice that there are some divisors that both have in common: 1, 2, 3, and 6. We call these common divisors of 18 and 24. What we're most often interested in is the greatest common divisor, the largest integer that evenly divides both a and b. So in this case, the greatest common divisor, or GCD for short, is 6. Now suppose we were to list out the multiples instead. We can also find the least common multiple, or LCM, of two numbers. And there's two ways we can do this. First of all, as we've done here, we could list out the first number of multiples of 18 and 24 and see when they first have something in common. But this can be tedious. The other way is much quicker. Simply multiply the two numbers and then divide by their GCD. There's our least common multiple right there, 72. So an interesting identity to note is that the greatest common divisor of two numbers times the least common multiple of those two numbers is equal to the product of those numbers themselves. The greatest common divisor, in a way, tells you what two integers have in common. Now, as you probably know, 1 will be a divisor of any integer. So sometimes we may run across two integers for which 1 is the only divisor they have in common. If a equals 9 and b equals 10, then the factors of a are 1, 3, and 9, and the factors of b are 1, 2, 5, and 10. When the greatest common divisor of two non-zero integers a and b is only 1, then we say that a and b are relatively prime. Now, all this is good if you can actually find the greatest common divisor of two numbers. For 18 and 24, this was a pretty easy task. But what if I wanted to find the GCD of these two numbers? It would take a long time just to find the factors of each of these, and then even more time to figure out what the largest factor was that they had in common. Fortunately, Euclid came up with a much more efficient method for finding the GCD of two numbers, by doing repeated division. Today we call this method Euclid's algorithm. Here's how Euclid's algorithm goes. Let's say our two numbers are 309 and 21. First, we divide the larger number by the smaller number using Euclidean division, and we find that 309 equals 14 times 21 with a remainder of 15. Now what we do is we take the smaller of the two numbers and divide it by the remainder that we just got. So now we've got 21 divided by 15. Well, 21 equals 1 times 15 with a remainder of 6. Now we do it again, dividing 15 by 6. This time we get 15 equals 2 times 6 with a remainder of 3. And we do it again, 6 divided by 3. So we get 6 equals 2 times 3 with a remainder of 0. Stop. Once you've gotten a remainder of 0, you can't go any further. So the last remainder you got before 0 happens to be the greatest common divisor of your original a and b. In this case, the GCD of 309 and 21 is 3. Take a moment to think about just how profound that result is. We've managed to find the greatest common divisor of two numbers without ever finding any actual divisors of either number. Another neat yet important property of greatest common divisors is that you can always express the GCD of a and b in terms of a and b. Specifically, if d is the greatest common divisor of a and b, then we can always find m and n such that d equals m times a plus n times b. We call d a linear combination of a and b. Not only is it always possible to do this, but Euclid's algorithm actually paves the way. Let's represent 3 as a linear combination of 309 and 21. First, we need to use Euclid's algorithm on these two numbers. Next, we solve for all the remainders. So 15 equals 309 minus 14 times 21, 6 equals 21 minus 1 times 15, and 3 equals 15 minus 2 times 6. Now what we do is we look at our bottom equation. See how the GCD is on one side? What we do now is we start substituting the remainders from the equations above into the bottom equation, one by one, working our way up until we have our linear combination. Be careful when doing this not to multiply anything out or simplify until the very end. So let's begin. 3 equals 15 minus 2 times 6. Well, 6 is our remainder from the next equation above it, so substitute that into the bottom one. Now 3 equals 15 minus 2 times 21 minus 1 times 15. Then 15 is the remainder from the next equation up, so substitute that into the 15s. Now we've got 3 equals 309 minus 14 times 21 minus 2 times 21 minus 1 times 309 minus 14 times 21. Wow, that's a lot. The last thing we have to do now is multiply the whole thing out but make sure to keep 309 and 21 intact so that we can group our copies of 309 and 21 together. After some algebraic manipulation, we get 3 equals 3 times 309 minus 44 times 21. And there we have it. If we let m equal 3 and n equal negative 44, then 3 equals 309 times m plus 21 times n, just as we wanted. This method of expressing the greatest common divisor of two numbers as a linear combination of those two numbers is essential for a famous class of equations called Diophantine equations, named for the aforementioned Diophantus. When we're solving a Diophantine equation, we're only looking for integer solutions. Fractions and such aren't allowed. These sorts of equations pop up all the time in real life, such as the balancing of chemical equations. The most basic type of Diophantine equation is of the form ax plus by equals c, where a, b, and c are integer constants. So, suppose we were given the equation 309x plus 21y equals 9. Sure, there are plenty of solutions to this equation. Just pick a value of x and solve for y. But are there any integer solutions to this? While before this might have been accomplished with a great deal of trial and error, it turns out that with a little elementary number theory, we have all the tools we need to solve this problem. We already know that the greatest common divisor of 309 and 21 is 3. And we just saw that we can express 3 as 3 times 309 minus 44 times 21. So what about 9? Well, 9 is 3 times 3. So that should be 3 times our expression, which we can distribute to the coefficients. So there is in fact a solution. Let x be 9 and y be negative 132. We have in fact found a solution. In fact, we'll always be able to find a solution, as long as our number c is a multiple of the GCD of a and b. That means that, for instance, the equation 309x plus 21y equals 8 would have no integer solutions, since 8 is not a multiple of 3. Or for a somewhat more readily visible example, there would be no integer solutions to 4x plus 6y equals 9. No matter what x and y are, 4x and 6y will be even, so there's no way they could add up to 9, which is odd. By the way, our solution we found to our equation isn't unique. There are actually infinitely many others. Suppose we make d the greatest common divisor of a and b, and suppose we found a solution x0, y0 from using Euclid's algorithm. Then every other solution of the Diophantine equation will be of the form x equals x0 plus b over d times t, and y equals y0 minus a over d times t, where t can be any integer. So a few more solutions of our equation would be 16 and negative 235 when t equals 1, 23 and negative 338 when t equals 2, and 2 and negative 29 when t equals negative 1. Now it's time to delve into what is probably the single biggest and most mysterious topic in all of number theory: prime numbers. A prime number is a natural number with exactly two positive divisors, the number itself and 1. They begin with 2, the only even prime number, after which all are odd: 3, 5, 7, 11, 13, 17, 19, and so on. Be careful. Note that 1 is not a prime number. I'll explain why in just a bit. Anyway, on the other hand, a composite number is one with more than 2 factors. For example, 6 has 2 and 3 as factors, in addition to its trivial divisors 1 and 6. The prime numbers, as rare as they are, go on forever without end, as we proved in the lecture on proofs. Euclid proved this by contradiction. The prime numbers can be thought of as the building blocks on which the entire set of natural numbers is built. Recall that when we talked about strong induction, we were introduced to the fundamental theorem of arithmetic, which states that every number can be represented as a unique product of powers of prime numbers. This is actually the big reason that 1 cannot be a prime number, though it used to be considered a prime number for a long time. If we allowed 1 to be a prime number, then we would no longer be able to have unique prime factorizations. Take 15, for example. We know we can represent 15 as 3 times 5. But if we allowed 1 to be a prime number, then it could also be written as 1 times 3 times 5, or 1 times 1 times 3 times 5, or 1 times 1 times 1 times 3 times 5. You see where this is going? So we can't allow 1 to be a prime number. The prime factorization of a number will be of the form p1 to the e1 times p2 to the e2 times p3 to the e3, and so on, where p1, p2, and p3 are the prime numbers, and e1, e2, and e3 are non-negative integers. Remembering that anything to the 0 power is 1, we can actually see that there are hidden powers of every prime in the prime factorization. It's just that the powers will be 0 for a good number of these primes. So 45 can be thought of as 2 to the 0 times 3 to the 2 times 5 to the 1 times 7 to the 0 times 11 to the 0, and so on, with every other prime number from then on having a power of 0. We can also use prime numbers as an alternate way to find the greatest common divisor and least common multiple of two numbers. Suppose we have two numbers a and b, and we know their prime factorizations. Let's use e1, e2, and e3, and so on for the powers of the primes for a, and f1, f2, f3, and so on for b. Then to find the greatest common divisor, we multiply the lower power of each prime together, and to find the least common multiple, we multiply the higher power of each prime together. So let's look at our original example of 18 and 24. 18 is 2 to the 1 times 3 to the 2, and 24 is 2 to the 3 times 3 to the 1. So the greatest common divisor takes the lowest powers, 2 to the 1 times 3 to the 1 equals 6. And the least common multiple takes the highest powers, 2 to the 3 times 3 to the 2 equals 72. This method extends to 3 or more integers too. Just take the lowest or the highest out of all of them to find the GCD or LCM respectively. Another useful thing that comes out of prime numbers is a discovery of Euler's called the phi function or totient function. Phi of n is defined as the number of positive integers less than or equal to n that are relatively prime to n. That is, the greatest common divisor is 1. So for instance, look at 12. The only numbers that are relatively prime to 12 are 1, 5, 7, and 11. That's 4 numbers total. So the Euler phi of 12 is 4. Now, given some n, how could I calculate phi of n? We can use the prime factorization to find out. The prime factorization of 12 is 2 to the second power times 3 to the first power. So, since 12 has a 2 in it, any number that also has a 2 will have a greatest common divisor of at least 2, if not some higher power of 2. Half of the numbers from 1 to 12 fit that description, so the other half will not have a 2. So we take out half of the numbers from 1 to 12, leaving us with 6 of them left. Now let's look at 3. Any number with a 3 in common will have a greatest common divisor of at least 3. So since that fits 1/3 of the numbers, the other 2/3 won't have a 3 anywhere in the list of divisors. So, if we start with 12, multiply by 1/2 to get rid of the multiples of 2, and multiply by 2/3 to get rid of the multiples of 3, we end up with 4 numbers that are relatively prime to 12. This same method will work to find the Euler phi of any natural number n, given its prime factorization. For every prime p sub I that is a factor of n, multiply n by p sub I minus 1 over p sub I. Notice, by the way, that this means that if p is a prime number, then Euler phi of p is p minus 1. So primes are apparently quite useful for all sorts of reasons. But the question remains, how do we actually find whether a number is prime or composite? We do know some things about the distribution of the prime numbers. The prime counting function, pi of n, not to be confused in any way with the half-circle constant pi from trigonometry, is the function that counts the number of primes less than or equal to some real number x. So for example, pi of 12 equals 5, because there are 5 prime numbers less than or equal to 12, 2, 3, 5, 7, and 11. At the end of the 18th century, two mathematicians, the German mathematician Carl Friedrich Gauss and the French mathematician Adrien-Marie Legendre, conjectured that the prime counting function was approximately equal to, or technically asymptotic to, x divided by the natural log of x. This was later proven in 1896 by French mathematician Jacques Hadamard and Belgian mathematician Charles de la Vallée-Poussin, independently of each other, and is now known as the prime number theorem. So this gives us at least some idea of how rare the primes are, though it further supports the fact that the prime numbers are in fact infinite in number. X over log x does in fact keep growing, even though it does so quite slowly. One of the earliest methods to actually find prime numbers dates back to ancient Greece, and is attributed to a mathematician named Eratosthenes. The method is called the sieve of Eratosthenes. Here's how it goes. First, list all the numbers from 2 to some number. In this case, let's go up to 100. Now the first number on the list is 2, so we circle that number, and then cross out every second number until you reach the end. Now we look at the next number that hasn't been crossed out, 3. So we circle that and cross out every third number. And you repeat the process again. Each time you circle a number n, you cross out every nth number after that. Now the interesting thing is that after deleting all the multiples of 5 and all the multiples of 7, every single number is prime. This is because, as it turns out, once you circle a number that is less than the square root of your top number, everything from that entry on is actually a prime number. So since we went from 100, once we get past 10, everything is prime. See if you can investigate that a bit and figure out just why it's true. Now, while the sieve of Eratosthenes is great, it's not particularly efficient. We can't just plug in a really big number and expect it to find all the primes under it, and by big, I mean millions of digits long. It would take forever just to run. Isn't there a better way to find primes? Unfortunately, this time the answer so far is no, there isn't. As much as we do know about the properties of prime numbers, the most elusive thing about them is actually finding them, especially in a reasonable amount of time. For example, there's a set of equations that can determine if a number is prime, but it's a set of 14 Diophantine equations in 26 different variables. Yikes! In the 17th century, a French mathematician named Marin Mersenne found a number of primes of the form 2 to the p, where p is a prime number. It was believed that this expression would be prime for all primes p, but alas, this was not the case. The smallest counterexample is 2 to the 11th power minus 1, 2047, which is 23 times 89. Even though his list was not entirely correct, nowadays we call these sorts of prime numbers Mersenne primes. Today we know a total of 48 different Mersenne primes. Since 1996, as the size of these Mersenne primes has gotten astronomically huge, the quest for larger and larger Mersenne primes has been carried out by what is known as the Great Internet Mersenne Prime Search, or GIMPS for short, which runs on computers all over the world to try to find the next one. The largest known Mersenne prime was actually discovered quite recently, in January 2013, by Curtis Cooper at the University of Central Missouri. This prime, the 48th Mersenne prime, is equal to 2 to the 57,885,161st power minus 1, and it has 17,425,170 digits. One rather interesting formula makes use of the floor function, which gives the greatest integer less than or equal to a particular number. So for instance, floor of 3 equals 3, because 3 is already an integer. Floor of 4.1 equals 4, and floor of negative 4.1 equals negative 5. We always round down on the number line. A mathematician named William H. Mills proved in 1947 that there exists a real number a, such that the floor of a to the 3 to the n is guaranteed to be prime for all positive integers n. What's more, we might know the value of a, which is about 1.306. But we can't be sure that this is the true value of a, because this value, called Mills' constant, is based on the assumption that one of the biggest unsolved conjectures in number theory, called the Riemann Hypothesis, is true. Let me explain what that is. The Riemann Hypothesis was proposed by Bernard Riemann in 1859, and it's based off his Riemann zeta function. The Riemann zeta function is studied in depth in complex analysis, which goes into the many intricacies of complex numbers. So I won't go too deep into it here. I'd like to just try to give you a general idea. Suppose z is a complex number. Then if the real part of z is greater than 1, then the Riemann zeta of z is equivalent to the infinite sum of 1 over n to the z. That is, 1 over 1 to the z, plus 1 over 2 to the z, plus 1 over 3 to the z, and so on. It takes quite a bit of work to extend this formula so that it's defined for other complex values, but eventually it can be defined for all values of z except for the real number 1. Now, zeta of negative 2 happens to be 0, as is zeta of negative 4, zeta of negative 6, zeta of negative 8. In fact, all negative even numbers are zeros, which we call the trivial zeros of the Riemann zeta function. There are non-trivial zeros too, though. For instance, giving approximations to 3 decimal points, there's 1/2 plus or minus 14.135i, 1/2 plus or minus 21.022i, 1/2 plus or minus 25.011i. Noticing a pattern? The real part of all of these is 1/2. But is that always the case? The Riemann hypothesis conjectures that this is in fact true, that the real part of all non-trivial zeros of the Riemann zeta function must be 1/2. This conjecture is another one of the 6 remaining Millennium Prize problems, and as such has a $1 million price tag associated with it, probably because if the Riemann hypothesis were to be proven true, it would have huge consequences for the distribution of prime numbers. The big thing to take away from this is that the prime numbers are one of the oldest mysteries known to mathematicians, and even with all the developments we've made throughout history, they still elude us. For cryptographers, though, that's a good thing. It's enormously difficult to factor large numbers that are the products of 2 primes, even for today's computers. This difficulty is the basis of what's called RSA cryptography. And on that note, we'll finish this lecture and resume next time with a particular topic in number theory called modular arithmetic. We'll talk more about RSA cryptography then. See you next time.